All right, so let's take a look at our energy balance. We already derived the whole thing yesterday, so I'm not going to rederive the energy balance. I'm just going to rearrange it in a little bit of a minor fashion. So if you keep an eye on the energy balance as we derived it yesterday, you'll see where all of these terms are coming from. The first thing that we're going to do is move that delta H term over onto the left-hand side. We're going to leave it in terms of conversion for the moment. So the only thing that's going to show up over on the left-hand side is going to be that term with conversion times our delta H. I put the negative sign in there. You'll see why the negative sign has to be there if you look up in your notes, because it was already negative on the other side and I moved it around over here. And we're going to just set that equal to everything else that was left inside of our energy balance, with one exception. There's an FA naught that was floating around inside in front of this. So if you look in your notes, the way this would have been written is with an FA naught right there, and it would have been plus as well, but I've moved the, actually it would have still been minus, but I moved it over to the other side and then added a minus again. The other thing that is odd in this case is I'm going to move FA naught to the other side for no reason other than I want to be able to talk about these with a particular set of units on them. So I'm not going to keep that FA naught over here. I'm just going to divide everything on the other side by FA naught. So over here, you'd have minus UA over FA naught, T minus TA, minus, actually the FA naught goes away because that one cancels, CPA times T minus T. This was the 0 that I had messed up last time. So if you look a little higher in your notes, you would see that. Actually, we can't put that negative over there just yet. Can we? I don't think so. Because we had a minus FA naught there. No. We got to leave that positive for now. Because otherwise your signs won't work out from your previous one. So that should look pretty much the same as the energy balance that we saw before, except I've moved the X delta H over to the left-hand side instead of the 0 that we had before. And I divided everything through by FA0. So there used to be an FA0 sitting in front of this term as well. But again, I divided all the way through by FA0, so we don't have it. The reason for that is because now these terms all have units of something that looks like the units on delta H. So the units all look something like joules per mole. So we're basically talking energy on each one of these. If you had left the FA naught in there, that would be okay. Then it would just have units of something like joules per second, which is like power. Still fine. You'll still end up getting similar results. Why did we do something like this? These are going to be the two sides of the equation that we're going to deal with. There are common names for each one of these. The names are as follows. G of t is defined as minus delta H times X, or XA, whatever it happens to be. And this refers to, it's kind of a weird word for it, but I get what they were going for when they came up with it. Heat generated, actually not heat, I'm going to overrule your book there and not call it heat, energy. Heat is a specific way that we transfer energy back and forth. What do we mean by heat generated? That means that anything that was associated with enthalpy changing due to the reaction is coming from that G of T term. So when we break, for example, a double bond, that energy has to go somewhere. We don't exactly know where it's going, but it got quote-unquote generated. The other side is everything else. So the other one is R of t. That's all the stuff on the other side. So that's defined as UA over FA naught T minus TA plus the sum of all the theta i's times CPI times T minus T0. So we put the theta I back in there. For our example, there was only one theta, and that theta was 1. But we're just writing it in a more general form here in case there's more species that are available. This, by the way, is why G of t has that negative sign sitting in front of it, just so that R of t can look like a bunch of positive numbers instead of having those negative signs out front. Granted, a little weird. I don't know why they chose to do that, but that's the way they chose to do it. R of t is another one I'm not really sure I agree with their word for this, but the reason it's called R of t is because this refers to energy removed. Personally, I prefer the word energy absorbed, so I'll put this down here in the bottom. Either way, what they are referring to is where does that energy go? I generated energy when I broke those bonds or rearranged the molecules somehow if I didn't have to break any bonds. That energy has to go somewhere. It can go one of two places. Either it can go into the reactor itself, all of the components inside the reactor, and that represents this, or sorry, that's represented by that theta I CPI term, right? The things inside the reactor act like a sink for that energy. They can absorb that energy and raise their temperature. That's one place the energy can go. The other place the energy can go is out through the jacket, and that's the UA T minus TA form. So you can just simply remove the energy from the system altogether. And that's about the only two places that we can put our energy. If you think of things like maybe it wants to vaporize, that would be somewhere inside the R term. We've assumed all throughout the class that we never change phases within our reactors, so there's no enthalpies of vaporization that are inside here. But those would still count as terms inside the R, energy being removed from, essentially the reaction itself. That's why I don't really like the word removed in that case. It doesn't mean it came out of the reactor. It just means it came out of the molecule somewhere and went somewhere else. That's why I like the word absorbed, because it can be either absorbed by all the molecules and raise their temperature, or it can be absorbed by the coolant that was jacketing the reactor to begin with. So these represent that third form of how to solve nonlinear equations, which is to separate it into a function on the left-hand side, a function on the right-hand side, and then look for intersections between those two functions. The intersections between G and R have some meaning. It's not so much the intersections themselves, but the areas right outside the intersections, and that's what we're going to look at. The plot that I'm about to draw, give yourself a fair amount of space for this plot, because we're going to annotate the crap out of it. There's going to be tons of annotations. I might have to erase some annotations, because I don't know that I can fit them all. And I just pray the iPad does not crash halfway through writing this. So what do? We set it up in the same way that we would if we wanted to solve any other nonlinear system, using that same f of x is equal to gx form that we had produced. So on the y-axis, we're going to plot either g of t or r of t. And I'm going to try to color code these. Let me try and find some red ink. Here's some red. Is that the shuffle of people getting out colored pencils and stuff? So we've got G of t here. Is that red clear enough? You want me to brighten up the red a little bit? I hear you. Let's brighten up the red. How about that? Kind of pink, whatever. Let's go with it. We've only got 20 minutes left. We'll keep going. So it is either G of t on the y-axis or R of t. So I'm going to color G of t as kind of the pinkish red color because we're going to think of that as energy being generated. So I associate that with like hot. And R of t as the energy removed, which I associate with kind of like cold. It's not really cold, but that's why I'm choosing red and blue here. And then on the x-axis, we're going to plot temperature. So for example, we could plot that temperature over the same range that we did previously, so maybe 250 to like 700, something like that. And we're going to get two curves that show up on here. We're going to get an R curve, we're going to get a G curve. There's something very interesting about both of those curves. The interesting thing about both of those curves is that R of t is linear in temperature. So if you look at the places temperature shows up, it shows up right here in a linear fashion, and it shows up right over here in a linear fashion. So if I plot R of t as a function of t, it's going to be a straight line. It's going to be angled somehow, and it's going to have some kind of an intercept, but it's going to be a straight line. The other one, G of t, is not going to be a straight line because of this x term. So the x term that's sitting inside there could be rewritten as, for example, RA V, I think over FA naught is what that could look like. And this term is not always linear, right? You can have some kind of nonlinearity in there due to whatever reaction you happen to have. Yes?
Would the R term still be linear if there was co-flow or counterflow TAs?
Yes. Specifically for a CSTR, yes. In a CSTR, it won't matter if there's a co-flow or a counterflow. In fact, we usually don't define a co-flow or a counterflow.
So in a CSTR, is there always constant TA?
For all practical purposes in this class, yeah, we're going to assume a constant TA. Yeah. Also, the other assumption that's in there, if the CPIs are not constant, then it's possible that could be nonlinear as well, but we're going to assume that they're constant. Not necessarily equal for everything, just constant. So your R of t is going to be a straight line, your G of t is not going to be a straight line, and so we're going to get something like this. Let's try to pretend, bear with me, that this is a straight line. Hey, that's not bad. That's pretty good, right? Freehand straight line. So there's our R of t. Your G of t is not going to be a straight line. It's going to be some kind of a wavy line. Exactly what that wavy line looks like, you just got to plot it and see what it looks like. If we were to actually plot our wavy line, I'm going to exaggerate it a little bit. It would look something like that. And so we see right away that there are three intersections, as we saw in the previous one. Here, here, and here. And if you were to solve for those particular temperatures, you would get exactly the same temperatures that we had solved for just a moment ago. The advantage of doing it in this particular way is because now we have some intuition about what happens when G is higher than R or R is higher than G. If we take, for example, over here, what happens if, for the moment, R is greater than G? If R is greater than G, it means you're removing energy from the, quote unquote, removing energy from the system faster than it's being generated by the reaction itself. And so if that is true, then T will go down. Because I'm either pulling that energy out somehow through the wall, or it's just being absorbed faster than it's being created. Not created. If you get into the location where R is exactly equal to G, then T is constant, right? This corresponds to the solutions that we had. If R is equal to G, we have satisfied the energy balance, and therefore we have our system. If R is greater than G, we have not satisfied the energy balance, and something has to change. We would need the full differential form to see exactly what that is, but we can see it graphically here in a moment. And then the other one is the only remaining option, which is what happens if R is less than G. What this means is your reaction is kind of going much at a rate such that it is producing energy much faster than it can be either absorbed by the species that are in there or removed by the coolant. And so if R is less than G, then we will see that T goes up. So we're generating lots of energy. Again, keep in mind this is kind of a qualitative description here, right? We're talking about the effects of time, even though the only equations that we're using are the steady state ones. So it's a little bit qualitative, but it certainly does work. So let's look at a couple of different regimes here and try to figure out what happens. Let's say that you pick a temperature right here. What does it mean to be at that particular temperature? Draw a vertical line at that particular temperature. At that particular temperature, we have that the red one is greater than the blue one, so that we have G is greater than R. If G is greater than R, that means we're generating heat faster than it can be removed, and the temperature is going to tend to go up. If the temperature tends to go up, that means we're going to walk our way up both of these lines. And it's just going to keep going up and up and up until we hit exactly this point, which is that stable point. What if it could keep going, right? What if somehow it started on the other side? Imagine drawing another line over on this side. Well, over on this side, we have the opposite case, which is that R is greater than G. If R is greater than G, we are removing heat faster than it's being produced by the reaction, and so the temperature is going to tend to cool. So we're going to walk back down that line. And guess what? We're going to end up right at the same spot all over again. So if we're slightly above that steady state point, this one was 618. This was our 618 Kelvin. That point is what we would call a stable steady state operating system. So this one is stable. The reason that it's stable is because if you slightly perturb the system, right, suddenly your coolant flow rate goes down a little bit, or your reactant conversion goes up a little bit because there was a hot spot or something like that, it'll kind of wiggle around on that steady state position a little bit, but it'll always push itself back to where it used to be, assuming all your whatever got jiggled in the system went back to where it was before. So that particular state is stable. You can also see that the one down there on the bottom is going to be stable as well. So this was our point down here, which was, let me pull up our temperatures. This temperature was 326. So we can try to determine if that one is stable or not by looking at what happens on either side of that intersection. So if we look on the left-hand side, G is greater than R, so that's going to tend to increase the temperature because the rate of generation is higher than the rate of removal. So that's going to tend to walk to the right. What happens if you're at that point and you get shifted a little bit to the right, to a higher temperature? Well, now R is greater than G, and so we're removing energy faster than it's being produced by the reaction, and you're going to fall backwards to that point again. And you can see all of those points are merging onto that single temperature. So 326 is also a stable operating point. So if you were to somehow set your reactor up such that it was operating at 326, you could come along and kick your reactor and give it a little shake or something like that. It might perturb a little bit off of that as it kind of wobbles back and forth on these curves, but eventually it will find its way back to that particular operating point. The one in the middle, though, is different. So the one in the middle, you've got points going this way on the left, and you've got points going this way on the right. So if I am at that point, and that temperature was 442, if you are right at 442, 442 by itself is a valid, yes?
Are these the same as the Lagrangian points?
No, they're a little bit different. If you are right at 442, you are technically at steady state. However, that's like trying to balance a pen up on its point. Right there, let me see if I can do this. That is a stable system, or not a stable system. It's an equilibrium system, right? It has satisfied, in this case, the conservation of forces. balance of forces. That 442 does satisfy both the material balance and the energy balance. However, if you disturb it at all, if you come along and change one of the flow rates a little bit, somehow the reaction goes a little bit faster because it got like a hot spot or something like that, and it shifts at all off of exactly that point at 442, it will then fall to one of those two stable points. If you somehow made the temperature even just a fraction of a bit higher than 442, it will find its way up to 618. If you made it even a fraction smaller than 442, it will find its way down to 326. And so we call that particular point an unstable point. And so these are the points that you have to consider when you've got a diagram like this to decide which one is the one that I'm actually going to operate at. If you haven't started your system up yet and you don't know anything else about what the temperature is or could be, then you have some tools that can allow you to determine which of those states you want to operate at or which of the states that you will operate at. One of the tools that you can use for that is to change your coolant temperature. Is it coolant temperature? No, your inlet temperature of your streams. So actually, no, coolant temperature would be fine. You could change, for example, FA0, because that will shift your R curve, and we're going to see what happens when we shift the R curve in a minute. You could change TA if you wanted to. That would shift your R curve. You can't really, I don't know, most people would not assume that you can change your CPs. They're kind of like constant. You could presumably change your theta I's, right, if you change the flow rates of stuff coming in. Or you could change your inlet temperature over here. If you change any of those, and by change, I mean if you're actually sitting in front of a reactor, these are things for which there's probably a knob sitting around somewhere, and you can just like push the knob and make one of those things change. For example, area, you can't just walk in front of a reactor and change the area, right? It's kind of fixed, it's an area. You could change any one of those and start moving R back and forth. What's the advantage of moving R back and forth? Keep in mind it's a straight line. Let's say that we want to change T0 over on the right-hand side. If you change T0, you're going to shift that operating line, or sorry, the R line, and so it might look something like this. So I'm going to have to change here. So this would be what it could look like if you change T0. What is the advantage of changing something like that? Well, if you continue that G curve out a little bit, you now only have one intersection that's up here. So this is your new operating point if you were to change T0. So you can shift that whole R curve over to the right if you change T0. You now only have one point that satisfies all of those. Your reactor will work at that particular point. And now what do? You start putting that T0 back to where it was before, and you will shift back over to your original curve, operating at the higher conversion. You can do it the other way around too. If you change T0 in a different way, you can force that T0 line to be above all of those points. Remember, it's got to have the same slope if we're just changing T0. Right, so you could shift it this way so that there's some other intersection out here. And then shift it back to what the original T0 was so that it slowly goes over to the very low 326 point. So depending on how you start the system up, you can dictate which one of those 2 points you're going to get to. You're going to have a really hard time getting to that center point. There's not a great way to get to the center point, nor should you want to get to that center point because it's not stable. You'll just cruise right through it and hit the other stable point on whichever opposite side that you have. So we can see how both of these work over in the code that we had a minute ago. I guess I will leave that up for a moment because I know we wrote a lot on there. While I leave that up, I'm just going to code the G and the R inside MATLAB to give you a chance to finish up everything there that I've got. Okie dokie. Everybody got everything on there? I'll switch back over. Okay. So we'll take a look at both what that actual squiggle line looks like for our system and then show how you can fiddle around with T0 and get those things to look a little bit different. So I've got my G of T here, I've got my R of T here. I just need to take that and divide by FA0 here and get rid of the one over here. And then we're going to plot G as the red line from 250 to 750 and R over the same range as a blue line. Oops, forgot to clear everything. There we go. So there's our wavy lines, like we saw before, a G and an R. We can add that legend on there. G, R. There's my legend. So what happens if we change T0 by a little bit? We can what was the original T0 that we had? 325. Right here, let's say T0 is not 325, but say 300. Oh, I have to call hold off or all these things are going to plot right on top of themselves. So 325 didn't, or 300 didn't have a big effect. Let's go down to say 280. Not a big effect. 150. Oh, closer. I'm not sure we can get low enough on that side. 100. You see what's happening to the blue line as we're doing that? The blue line is shifting further and further to the left. Let's take a big jump and go all the way down to 10. Right? The blue line is shifting further and further to the left. We can't actually operate at 10 degrees. Can we go all the way down to 1? Even if we go all the way down to 1 Kelvin, we can't get that line to go all the way over on the left. So we're probably never going to be able to operate down here at the bottom one, which is kind of fine, right? Nobody really wants 1%. Let's reset it back to 300, which was our starting point, and see what happens if we increase the inlet temperature. So instead of 300, we'll do 350, a little bit to the right. Let's take bigger steps, 450, closer, 550. We're getting there. 650. Oh, so close. So you can see now, I'm going to stop recording over here. Sorry, screencast, we're done.